Hi everyone and welcome back to the physics module. Over the last few lessons, we've built a lot of different skills across various fields. But to understand how a quantum computer processes information, we first have to understand the microscopic world. And to do that, we have to answer the question, what exactly is the universe made of? For centuries, physics was successful because it divided the entire universe into two completely separate, strictly defined boxes. Everything you could touch, see, measure, or interact with had to fit perfectly into one of these two boxes. On one hand, we had matter, and on the other, we had energy. So let's look at the strict rules classical physicists built for these two different realities. First, let's focus on matter, which is fully made up of particles. You could think of a classic particle as a microscopic ball, which means that it satisfies a few requirements. First, it's a discrete, solid chunk of physical stuff with a specific mass. Because it's a discrete chunk, you can count it. You can hold exactly one particle, or two, or 10, but you can't hold one and a half, or a cloud of smeared particles. In other words, it has distinct physical boundaries. Second, a particle is localized. This means that it exists in one exact set of coordinates at the universe at any given time. If you roll a ball across a table, for example, it travels in a straight predictable line, and if it hits a wall, it hits exactly one specific spot on that wall. Many physicists, including Newton, believed that light itself belonged in this box. He argues that a beam of light is just a stream of tiny microscopic particles, which he calls corpuscles. So if you turn on a flashlight or light a candle in Newton's case, he basically believed that you were firing a machine gun of tiny light particles across the room. But on the other side of our dividing line, classical physics stated that energy, things like sound and heat, behave as a wave. A wave is fundamentally different from a particle. It isn't a solid, countable chunk. It's a continuous, smooth flow of energy which spreads out throughout space. The best way to visualize this is to picture throwing a rock into a pond. When the rock hits, it doesn't just create a localized object. Instead, it creates ripples which spread outward in expanding rings. But the implication of this is that waves do something that particles absolutely cannot do. They interfere at each other. If you throw two baseballs at each other, they'll just hit each other and bounce off. But if you create two overlapping ripples in a pond, the waves pass right through each other. Where two high points, or crests, meet, they add up to create a bigger wave, and where a low point meets a high point, they cancel each other out, leaving the water completely flat. By the early 1800s, a physicist, Thomas Young, ran a famous experiment shining light through two narrow slits. But the light didn't behave like a barrage of bullets. Instead, it created an overlapping interference pattern on the wall, exactly like ripples in a pond, which contradicted the idea that light is a collection of particles. And then again, in the early 1900s, scientists started doing experiments which broke down this distinction further. The first major flaw in the classical model came from something called the photoelectric effect. Scientists discovered a strange phenomenon. If you shine light onto a piece of metal, the light can actually knock electrons completely out of the metal, creating a tiny electrical current. At first, they assumed that the light was acting like a standard wave. They figured that if they just made the light super bright, then it would hit metal harder and knock out more electrons, regardless of the wavelength of the light. But that isn't what happened at all. They found that even if they shined a blindingly bright, intense red light at the material, absolutely nothing happened. Not even a single electron was knocked loose. But if they shined a really dim, really weak blue light at the material, electrons instantly flew off. Now, this makes absolutely no sense if light is a continuous wave. To understand why, imagine you're trying to knock over a heavy car. Red light is like a stream of tiny, lightweight marshmallows. If you throw a marshmallow at a car, it just bounces off. Doesn't matter if you throw one or if you throw 1,000 at once. None of them individually have the energy required to knock the car down. Blue light, though, is like a heavy cannonball. You only need to throw one single cannonball, or a very dim light in our analogy, to knock the car over, because that one single object carries a massive, concentrated punch of energy. Einstein looked at this mathematical problem and proposed a new idea that light was actually hitting the metal in discrete, physical, countable chunks of energy. He called these chunks quanta, which we now know as photons. Einstein's discovery was a massive shock to the scientific community. Energy was suddenly acting like matter. Light, which everyone had agreed was a wave for over a century, was also a stream of defined particles. This brings us to the first major foundational law of quantum mechanics, wave-particle duality. The universe doesn't actually have these two separate boxes. The dividing line we drew at the beginning of this lesson is just a complete illusion created by our macroscopic human brains. Light and matter aren't strictly just waves, but they also aren't just strictly particles. To help wrap your mind around this, let's imagine a 3D cylinder floating in an empty room. If you shine a flashlight at the side of the cylinder, the shadow it casts on the wall is a perfect flat rectangle. But if you shine a flashlight from the top of the cylinder, the shadow it casts on the floor is a perfect flat circle. If you were a two-dimensional creature who could only see shadows, you'd be really confused. One day you'd run an experiment and then you measure a rectangle. The next day you run a different experiment and then you measure a circle. I mean, you'd argue forever about whether the object is truly a rectangle or truly a circle. But the real truth is, it's neither. It's a completely different, higher dimensional object that simply looks like a rectangle from one angle and looks like a circle from another angle. This is sort of what's happening in the quantum world. An electron isn't a particle, but it's also not a wave. It's simply a quantum object. In our next video, we'll be taking a closer look at a foundational experiment in quantum mechanics and learn more about the physical basis which underlies quantum computing. I hope to see you then.